start now, okay?
Mhm.
Today we are going to talk about the large-scale morphodynamic impact of groups of piers on lowland river. Here is our content. Okay, first we need to understand that bridge piers in river have a local scale impact and large scale impact. Local scale impact is local scarring of the bridge piers. This local scarring causes bridge failures. Let me tell you that 60% of the bridge failure in the United States since 1950 was due to local scarring. Between 1961 and 1976, 46 of 86 bridge failure in the United States was due to local scarring. For the large scale impact, there is bank erosion, sedimentation, and bar formation. This large scale impact could hinder navigation and block water intakes. Now we move to the research objective. Objective number one, reviewing the literature on local and large scale impact of bridge piers on river morphology, and also study how different engineering situations related to bridge pier installation like span characteristics, number of piers, and changing piers location affect the large scale morphodynamics of sandy lowland river. Objective number three is exploring mitigation measures, comprehending different configurations of bed cells. This leads us to the research questions. What are the results of previous researches in the field of local and large scale impact of bridge piers? Does the morphodynamic impact of bridge pier extend to the whole ridge? What is the large scale morphodynamic impact of applying different bridge piers configuration like span characteristics, number of piers, and location of piers on riverbed? Are bed cells efficient measures to mitigate the impact of bridge piers? Now we move to the literature survey. We have a lot in the literature, but here we put the most important points. First, about the local scale impact of the bridge piers, we could understand the flow structure around the bridge piers on its vicinity, as we can see on the right-hand side here. You can see here when you install a bridge pier in a river here, it creates a stagnation pressure and the acceleration of the flow at the upstream side, and this leads to downflow. This downflow impinges on the riverbed, creates a scour hole, and this scour hole triggers formation of horseshoe vortex, which entrains sediment further downstream. Also, there is a separation of the flow at the downstream side, which create wake vortices. This wake also entrains sediment further downstream. In our literature, also we have researchers emphasize that the span between the two bridge piers controls the size and depth of the local scour hole. Also, the shape of the bridge piers controls the depth of the local scour hole formed. We can review all of this in the thesis text. About the large scale impact, Musliman and Kislov, they proved that the local scouring affects the large scale morphology, as the local scouring alters the flow structure in its vicinity, and this affects the morphology on the macro scale in the river reach. Azhar and Kulsat also, they have a very interesting research related to large scale impact of bridge piers at morphodynamically stable and unstable system. They concluded that at morphodynamically stable system, a force bar is formed and it didn't migrate further downstream, while in the unstable system, it creates the bridge piers creates migrating bars that tends to migrate further downstream. They have also some results about the impact of using different discharge regime, sediment size, and lining bed in the cross section. Okay, now we come up to that's the plan. That's the general plan of our methodology. First, we choose a reference river, which is a reach downstream high Aswan Dam, Nile River, of course. Then we collected the data. Then we using the numerical simulation using 2DH model, which is Delft 3D. We build up our Nile River model, which we use for sensitivity analysis simulations and for calibration scenarios. We used many scenarios until the model simulate qualitatively the morphological behavior of the reference river. We take this calibrated physical and numerical parameters and use it for the numerical flume, which we use, we build and use in our research scenarios for bridge piers configuration scenarios and for also the bed cell scenarios. Then we come up with our results and conclusion. Now, here is the reference lowland river we use. As we said, this Nile River reach downstream has high Aswan Dam from kilometer 14 to kilometer 22 with a length of 8 kilometers. We have here a Aswan bridge at kilometer 19.07. The available data we have is a bathymetry data, 2007 survey. We have a daily average discharge data for the year 2004, also water levels, and we have sediment data that we could use in the model. Now here we come to the Nile River model setup. We use a curvilinear grid so that we can simulate the discontinuity in our reach and also the curvature of the Nile River. We could capture it more precisely. We have a problem of using because for Aswan bridge, the dimension of the bridge piers are small comparing with the main domain course. So we use different domains with different mesh sizes so that we can capture the Aswan bridges. So we used 3 domains with 3 different grid sizes and connected them using a domain decomposition. We used daily average discharge as upstream boundary, water levels as downstream boundary. Of course, we simulated bridge piers as thin dams. We use the value of morphological factor 40 after carrying out sensitivity analysis because our system is very slow. Okay, very fast, we carried out 14 simulations for the morphodynamic calibration. And here is I show on the right hand side here that's the best scenario we could get. As we see, it can capture qualitatively the bed formation of the actual bed. You can see here the alternate bars. It could form the alternate bars and pools on the other side. Simulation duration is 40 morphological years until the system reaches become steady and not and there is no further changes in the bed or negligible. On the left hand side here we have the hypsometric curve for the actual and the simulated bed. We can see here that on the lower elevations, which refers to the pool side, the curves tend to converge and they tend to diverge at high elevation, which refers to the bars. Okay, after that we set up our numerical flow model, which is a straight channel we use for our research scenarios. It's consists of rectangular grid as it is a straight channel. Also, we use the 3 domains, connecting them using domain decomposition, of course, for putting the bridge piers in the fine domain. A morphological factor of 40 is used after sensitivity analysis. We use a fixed piers dimension, which are 9.8 and 13.1 for width and length successively. Okay, how is it going? First, we set up our numerical flow, then calibrated physical and numerical parameters added, and then we added a groin 1 kilometer after the upstream boundary to form the alternate hybrid bar to make our river more realistic to the real river. And after the system reaches the steady state, we added bridge piers. But we have a problem here. The system reached the steady state after around 150 morphological years, which is a lot and complicates our model, take a lot of time. So we have to do something with that. So what we did is that we carried out initial bed model setup. We set up a new model with a coarse domain to simulate this instead of 3 domains. We use a simpler model and carry out the simulation until 150 morphological year with also morphological factor of 40. And after the system becomes steady, we put the bridge piers. We export this bed to our numerical flow model and put the bridge pier, carry out our simulation. We use this model also. It forms a weaving bed with hyperperiodic steady bars by placing, as we said, a groin 1 kilometer after the upstream. Here we have a video for the base case. Let's see it together. As you can see here, the groin here is triggering bed perturbation and forming here a forced bar around the groin and the migrating bars that tends to migrate further downstream, as we see, and elongated. After a time, the celerity decreased until it reached zero, and the system becomes steady with this hybrid bar, which we want to represent our research scenarios. Okay. Now here is the scenarios. Here is the base case, as we mentioned, that we use a discharge of the average discharge of the Nile River system we use. Also, we use the average river width. We use the number of bridge piers too, with a span around 33 meters, which means that bridge span over the river width ratio is 0.05. The bed slope and D50 we got from the data. Okay, first sets of scenario, we changed the span between the two bridge piers, which means changing this ratio. 5 scenarios. We have 8 scenarios changing the obstruction number of piers, which means changing number of piers in the transverse section, as we can see here. Also, we need also the third set of scenarios, the location of piers. In the base case, we install the piers in a transitional zone between two hybrid bars. We use another simulation to put it here in the zone where there on one side bar and on the other side pool. Okay. Now we come up the numerical analysis. We didn't just do a qualitative analysis for our work, but also we have a numerical simulation. We fixed an area in the vicinity of the bridge piers. We called it forced bar field. We fixed it for the all scenarios we carry out for the sake of comparison, and we generated a MATLAB script to compute the percentage of scour area in this field, the percentage of deposition height, the percentage of deposition area, the maximum amplitude of scour and deposition, and all simulation of course for 40 morphologically. Here is the first set of scenarios, span variation scenario. As you can see here from water depths for the 5 scenarios, as we can see at the first scenario at lower value of span, we can see the forced bar amplitude is higher than all other scenarios, as the flow between the two bridge piers is negligible comparing with the flow around this, and this means less flow velocity and less sediment transport and more deposition. Then increasing the span between the bridge piers makes the flow between the bridge piers more important, which means more flow velocity and more sediment transport and less deposition. We can have a look on the numerical analysis as well. We can see that here in these two charts, here is the relation between area of scour deposition and bridge span. Here is maximum amplitude of scour deposition with bridge span. We can see that the area of deposition in all scenarios is larger than the area of scouring, while the maximum amplitude of scouring is larger than the maximum amplitude of deposition. But also we can see that the area of scouring is localized, and among all 5 scenarios, also the maximum amplitude of scouring is localized among all 5 scenarios, while the maximum amplitude of deposition is decreasing, as we see in this, with increasing span, while the area of deposition is increasing slightly with increasing the span between the bridge piers. And here's what we just elaborated right now. Then next we come to the obstruction number of piers scenarios. We used, as we see here, from 1 to 16 bridge piers with different configuration, starting from the center line of the river. As we can see from here, increasing the number of bridge piers increase the amplitude and the area of the forced bar formed until a point. Then after this point, we see that the increasing the number of bridge piers decreased also the area and amplitude of the forced bar formed. We can see this also in the numerical analysis. We can see here the area of deposition increasing up to a point, and it decreases again at higher number of bridge piers. Also the scour area, also the maximum amplitude of deposition. The reason for that is we believe that at a higher number of bridge piers in the transverse section, the flow is distributed more uniformly, and the sediment transport is more uniformly distributed than in these scenarios, which means less deposition in area from another area, and this lead to like a total diffusion, as we see in the scenario with the largest number of bridge piers, while the maximum amplitude of scarring is increasing all the time. That's what we just mentioned here. The third set of scenarios, location of piers. We used, as we mentioned, two locations here at bar pool zone and a transitional zone. We can see that it forced bar formed here, and while here there is no forced bar formed. We can see from the numerical analysis also that as you can see, the deposition area, scour, and maximum scour height, all of this are larger in the transitional zone more than the bar pool zone. That means that the bridge piers in transitional zone have a footprint larger than the one in the bar pool zone. And the reason for that is that at bar pool zone, we install the bridge pier in a flow area dominated by a strongly varying cross-sectional profile. This generated by the presence of hyperbar. While here we put the bridge pier in a transitional zone in a flow area which is not much dominated by an existing bar structure, so the bridge pier can show its effect easily. Here is also a figure for cumulative bed level changes for the two scenarios. We can see here at the transitional zone the force bar and overall sedimentation and erosion. Now we come to the mitigation measures. We used three types of configuration for mitigation measure. We used a cell along the whole cross section, two side cells and one side cell in the pool side. We used R9, which has each 8 bridge piers scenarios to have a critical case. The crest level for all scenarios is the undisturbed bed before the installation of this bridge pier. The distance, we fixed the distance with 170.5 meter. Let's have a look at the result. As we can see here, R18, which refers to the two side cells, is the best measure. We can see that it could mitigate the force bar formation, as the force bar field redistributed the flow and redirected it in the middle where there is not a big resistance to the flow, and this could make more flow velocity in this area, sediment transport, and it would mitigate the force bar formation. While in the other scenarios they also mitigated, but not like this scenario. We can have a look here at the longitudinal section. We can see that in the scenario of two cells could mitigate the forced bar to far extent, but it also causes a local scouring in the vicinity of the bridge pier. On the bed cross section, here is we put also a cross section 13 meter upstream the cells. To see here is the cell elevation. We can see it could mitigate the forced bar forming here, and also a filling process on this side for the pool side, but also it causes a deposition on the other side. Okay, now here's the last scenario we will show here. Is we put a cell to mitigate the bar pool zone, as we see, to mitigate this cross-sectional variation between the bar and the pool here. The initial bed, we use the base case P1. The crest level is the undisturbed bed before the formation of hybrid bars and pools. We can see that the cell is successfully could redistributed the bed levels in its zone, as it could mitigate the hybrid bar here, and also could make a filling process for the pool side, as it redistributed the flow, as we mentioned before, so a higher flow velocity here, which could mitigate this force bar. And as you can see, the final cross section is more or less uniform around the undisturbed elevation we put for the cell. Okay, now we come up to conclusions. According to the numerical simulation, numerical analysis of our forced bar field, we can see that the bridge piers affect the whole reach as they increase deposition also to the hybrid bars of the reach with different intensities. The near bars are the most affected, of course. The bridge piers have a behavior of accumulating sediment more than scouring it, as we see that the area of deposition for all scenarios is larger than the area of scouring, regarding, of course, the forced bar field. The span between the two bridge piers and number of bridge piers in the transverse section, control areas, and amplitude of deposition and scouring, as we just seen the results. Also, piers in the bar pool zone have less impact on the bed morphology than piers installed in the transitional zone. We believe that bed cells are promising countermeasure against the large-scale impact of bridge piers, especially when you install them on two-side cells, and that's what we got from our numerical analysis, numerical simulation. Here is some recommendations for mitigating the large-scale impact of bridge piers. We advise keeping a relatively large span between bridge piers as possible. Also, distributing the bridge piers more uniformly in the transverse section to provide a more uniform flow among the bridge piers that could mitigate the deposition and the forced bar forming. Also, if it's possible, we recommend to install bridge piers in bar pool zone instead of transitional zone. But we know, of course, sometimes you don't have this choice, and the logistics controls you, and the design don't have an option to choose the location of the bridge piers. Also, installing bridge piers in bar pool zone that have some problems, because when you install like this, you have to put some piers in the pool side, which is very deep and requires a very deep foundation, and also make it more vulnerable for scouring. Here is a recommendation also for further studies. We need experimental and numerical verification for the results, especially the bed cell simulation. Because the bed cell simulation, we simulated only as a local weir in the Delft 3D, which is a subgrid structure that only represents the energy loss that happened due to the bed cells, and put it as quadratic friction in the momentum equation. So we need a better simulation to verify these results. Also, we need to consider different sediment sizes and the effect of bank erosion in our work. We assume the uniform sediment size and fixed banks. We need also to study the impact of using different shapes of bridge piers instead of only using rectangular piers, as we see that different shape of bridge piers affect on the local scale. We want also to check if it could affect on the large scale or not. We need to apply the study also on a real river case with enough data available. I advise to investigate the feasibility of using Delft 3D flexible mesh instead of using this Delft 3D with domain decomposition, because domain decomposition, it's complicated somehow. The model also, it has a lot of limitation and it's not very easy to use. Finally, we need more investigation about studying the effect of Hillis subgrid model in improving the large scale simulations.